Now we're going to find the antiderivative of this function, the natural log of x plus 1. We can use trial and error to find a formula, a general formula for this derivative. We can start by taking the derivatives of f and see what's going on. Okay, and the first derivative is going to be 1 over x plus 1. The second derivative is going to be minus 1 over x plus 1 squared. The third is going to be 2 over x plus 1 cubed. And the fourth one, okay, we're going to use this notation now, is going to be minus 6 over x plus 1 to the power 4. If we do 5, we're going to have 24 over x plus 1 to the power 5. Okay, how did I know this? I did them by hand. Okay, and I had to see what's going on to find a general formula here. I see that I can get something here. Look at the order of the derivative. Here I have 3. I have this power 3 here. Here I have the 5, I have 5. Here I have 4, I have 4. Okay, and also note that the sign here on top of the function, it changes. Okay, here for the odd, I have plus. For the even, I have minus. Okay, for the odd, I have plus. For the evens, I have minus. Okay, and notice one thing here. For the third order, I have this 2. For the fourth order, I have this 6. And I can see that I can get some relationship here, because 4 and 6 are related by, I can see by this rule here. Okay, here I can write 6 as 3 times 2. Okay, and I can write 24 as 4 times 3 times 2. Okay, and this is just the definition of the factorial. Okay, I can claim that the derivative of order n is here, it's going to be x plus 1 to the power n. I get this one from here. And on top, I get minus 1 to the power n plus 1 times n minus 1 factorial. Okay, so this is what I noticed. And I can go and check here. So for 1, I have minus 1 to the power 2, which is plus 1. I have n, which is 1. 0 minus 1, 1 minus 1, which is 0 factorial, which is 1. And here I have 1, x plus 1 to the power 1. For 2, I have minus 1 to the power 3, which is minus. And I have 2 minus 1, which is 1. 1 factorial is 1 over x plus 1 to the power 2. And it's true. In the same manner, I can check these orders. I can claim that this is my antiderivative of this function. To prove that, I need to use the principle of mathematical induction. Okay, that's what I'm going to do here. Okay, we're going to prove this statement here, that the antiderivative of this function is in this manner, can be written in this form. Okay, so we check that it's true. Okay, so we're going to call this one Pn. This is the statement. The antiderivative of f of x is given by this formula. So we have this one is true for n equals 1. We checked it. We assume that it's true for n, and we prove that it's going to be true for n plus 1. Okay? To prove the n plus 1 order, we assume that we have this one here. This is true. This is the induction hypothesis. And to go from here to n plus 1, we just differentiate. Because when we differentiate this one, the n order, we're going to get the n plus 1 order. Okay? So that's how we link the induction hypothesis with n plus 1 statement here. Okay, we have n, f of n of x prime. It's f n plus 1 of x. And let's differentiate this one. Here, this is just a constant. The one on top, it's going to be minus 1 to the power n plus 1 times n minus 1 factorial. And here, we're going to differentiate this function 1 over x plus 1 to the power n. Okay, when we do that, we're going to have minus n times x plus 1 to the power n minus 1 over x plus 1 to the power 2n. Okay, and when we do some simplification, this minus is going to go with this minus here. We're going to have minus 1 to the power n plus 2. The n here, it's going to go with the n minus 1 factorial. We're going to have n factorial. And we're going to simplify x plus 1 to the power n minus 1 over x plus 1. We're going to split these two n. We're going to add and subtract 1. And we split 2n into n plus n. So we have n plus 1 times x plus 1 n minus 1. Okay, I just added and subtracted 1, and I split these 2n into n plus n. Now we can simplify by this one, and I get minus 1 to the power n plus 2 n factorial over x plus 1 to the power n plus 1. Okay, and therefore this is true. Okay, so in my statement, when I change n plus 1 here, I should have minus 1 to the power n plus 2, and I have n factorial over x plus 1 to the power n plus 1. And this is what I have. That means the statement for n plus 1 is true. Okay, now we check that this statement is true for n is 1. We assume that's true for n, and we show that it's true for n plus 1. According to the principle of mathematical induction, this statement is true for any n bigger than 1. Okay? Now, what can we use this one here for?